Okay, I want to give you an introduction to polar, and really, polar is just another coordinate system that has advantages over, let's say, Cartesian or parametric. And so let's look at what polar is. And I guess to describe what polar is, I guess we can talk about what Cartesian is. You're used to what? Well, you're used to points, a point in space, and thus some curve having x and a y, right? Well, in a polar way, we're going to define this point, instead of its horizontal position and its vertical position, we're going to define it as the distance it is from the origin and the angle it makes with the x-axis. So me telling you r and theta is equivalent to me telling you x and y, right? X and y, I'm just telling you the vertical and the horizontal position. And now in a polar way, I'm giving you an r and a theta. And again, this is talking about a point in space. Let's just talk about that point. So that point's got an x and a y and an r and a theta. How are those related? Well, if you think about the vectors, so this is just the horizontal component. So how is x? Well, x is just r cosine theta, right? R is this position vector. And if you multiply by cosine theta, you get that adjacent piece. And so then y equals r sine theta, right? Kind of classic vector component breakdown. We also know the Pythagorean theorem is true. X squared plus y squared equals r squared. Again, that's for any point on that polar curve. We also can say that theta is inverse tangent of y over x, as long as we're using the angle with respect to the x-axis. So we can get kind of some basic breakdown between the Cartesian and a polar kind of system. Eventually, we'll look at all sorts of calculus things in terms of the polar, but let's just start right now thinking about what a polar curve is. Okay, so Cartesian curves, f of x. So here's an example of some Cartesian curve, like y equals x cubed plus 2x, right? That's some cubic function, and we know its general shape. And we say y equals, but we really mean f of x, right? That's some Cartesian, right? And then in a polar way, we might define some polar curve as r equals 2 theta plus 1. And we say r, but we really mean r is some function of theta. Now we all know what that cubic looks like, right? That's some shape that kind of, looks like some cubic function. And again, it's a collection of points x comma y. But now this is a collection of x comma y points. However, its restriction tells us how the angle is related to r, right? How does r relate to the angle? Well, you can kind of think about starting to graph these by just looking at a theta and r chart, just like you would. How would you originally have graphed this? Right, before you knew anything about functions, you would have done some maybe x, y chart, and you would have plugged in like -2, -1, 0, 1, and 2 for x, and you would have found the corresponding y values, you would have plotted these points, and then you would have connected the dots. Well, before you get too comfortable with polar, you might have to do something like that. And so if you do some theta r chart, theta is the amount you've rotated, and then r is then that distance. So when theta equals 0, and again, theta equals 0, we always start with the x-axis. That means we're pointing straight to the right, right? That's what an angle of 0 means. And what's r? Well, when theta equals 0, r equals 1. So plot that point, right? That's at an angle of 0 and an r of 1. And as we rotate, all right, let's rotate to 45 degrees, right? Pi over 4. Then we get 2 times pi over 4, which is pi over 2, which is like 1.5-ish. Plus 1, we get like 2.5. So now we're pointed, so this is around, 2.5-ish. So we're pointed at 45 degrees, and now we're out 2.5. Okay, so we're at that point. And then let's go straight up, right, which is pi over 2. When this is pi over 2, this is pi, which is 3.14 plus 1, so we're at like 4.1. So we're actually pointing straight up, and we're way out here. And as you can see, hopefully you get an idea that this thing is going to spiral, right? This is a spiral, because as theta grows, so does r, and as you rotate, you just keep getting further and further away, and you're going to keep spiraling. The rate at which you spiral is here. This is the kind of that vertical or horizontal shift in terms of you started at an r value. If that was 0, you'd start at the origin, and then you would have spiraled. And so polar curves can do all sorts of things, but r, the distance you are away from the origin, is some function of the angle of which you rotated, okay? just as a reminder, when we think about polar, this is 0, right? This is pi over 2, this is pi, this is 3/2 pi, and then we're back to 2 pi, right? You know, these are our 45s, pi over 4, 3/4, 5/4, 7/4, and so as we change our angle, our curve is dictated by how far we are away by this polar relationship rather than some Cartesian relationship. And that's really all polar is, and there's just lots of advantages sometimes in terms of how we have a curve of when we would use a polar relationship rather than some Cartesian relationship. Okay, so let's look at the calculus that we're going to do. All right, so the calculus. The calculus that we're going to do. Again, this is not, none of this is actually calculus, right? This is all just polar, and this is something you would look at in a pre-calc class. But the calculus of it, we're going to look at a bunch of things. So first thing, let's look at a dy dx. dy dx is and always will be the slope on the graph. So if you were interested in finding, let's say, the slope of the tangent line, right? So we wanted to come down here, and we wanted to find the slope of that line, we would need dy dx. So dy dx, very similar to parametric, is dy d theta over dx d theta. Now, what is dy d theta? Well, it's the derivative of y with respect to theta. So y is r sine theta. So let's use this example. What if we wanted to find the slope at this particular point? We would say maybe that's at 3/4 pi. So what's our y? So y equals r 2 theta plus 1 sine theta. So if we wanted to find dy d theta, we need to take this derivative with respect to theta at 3/4 pi, and it'd give us some number. So if we wanted to find dy d theta, we'd have to do product rule. So we'd have to do 2 theta plus 1 times cosine theta plus sine theta times this derivative, which would just be 2. And then we'd have to evaluate that at 3/4 pi, and then we'd have to do the same thing for x. X equals r cosine theta. So dx d theta would equal 2 theta plus 1 times negative sine theta plus cosine theta times 2, right? Product rule of x. And then we could look at dy d theta over dx d theta, and we could actually find then the slope of the line. If we wanted to know the actual x and y value at this point, well, then we just use the equation for x and y right here, right? We could find at theta, we could find r, and then once we know r, we could take r cosine theta, and we could get this x value and this y value. And if we knew the x value and the y value and the slope, then we could find the equation on the tangent line. So we can do all sorts of calculus things. Other things we can do in calculus, we can find dr d theta. Think about what that means. Dr d theta is the rate at which we change r with respect to theta. In this case, it's really easy. Dr d theta is just 2, right? And think about it, that's meters per radian. It's how fast it's the rate at which your radius is changing based on how you rotate. So this is saying that this is some constant increase of your r based on theta, which means you're increasing r by 2 meters per radian of rotation. So for every 1 radian of rotation you do, you're getting 2 meters further and further away from the origin. Right? A positive dr d theta means you're getting away from the origin. A negative dr d theta means you're actually getting closer to the origin, right? R is decreasing as you increase d theta. And this happens to be a constant, right? Lots of times dr d theta is some function of theta. But since we're spiraling out, it's some constant increase of r with respect to theta. Okay, we can find maxes and mins by looking for when dr d theta is equal to 0. If something was different like that, we then can actually say, well, what about dr dt? And they love asking that because that's how fast then you're rotating, or how fast r is changing, right? That's in meters per second. And so this is just classic chain rule. So that's dr d theta times d theta dt. So they'd have to tell you how fast you're rotating with respect to an angle, and then that would then tell you in meters per second in terms of what's kind of going on there. So you got all sorts of other things you can do with with calculus. Okay, well, what else can you do? Okay, well, we can find arc length. We can find arc length in polar. Arc length in polar, the length of the curve in a polar way. So we want to find the length of the spiral. We'd go from theta 1 to theta 2, square root of r squared plus dr d theta squared. And again, the derivation of that isn't too bad. It really is just the Pythagorean theorem. Very similar to all the other arc length stuff we've done. I'm not going to do it here, but if you want to look it up, you could just Google it. We can find the area of a curve, and I love this one, because what is area of a sector? Well, 1/2 pi, oops, sorry, there's no pi in there. 1/2 r squared theta. That's what the area of a sector is. And I want to derive that really quick just so you remember how easy that is. So take some circle, and we have some sector, okay? Right, we want to know this area. Again, I assume this is a perfect circle. It's not my best circle I've ever done. But the area of the sector is somehow proportional to the total area. But that proportion should be the same as the angle is to the total angle. Again, think about that for a second. I'm talking about finding the area of some fraction of the circle. The area compared to the total area should be in the same proportion as this angle is to the total angle, meaning 2 pi. So if we get rid of those pi's, and then take that half and this r squared and move it over, then we get this formula. And so what we do for polars, what's some polar curve? Well, polar, we have some, let's say we have that spiral again, and we want to find this area right here. Well, this r is not a circle anymore, guys. This and this are all different r values. However, the area of each one of these sectors can be written as 1/2 r squared d theta. And so what do we do in calculus? Well, we make this d theta infinitely small, and so these are infinite number of sectors here, and we divide them all up, and eventually, if you get enough of them, right, then the area really in polar is the accumulation of all these sectors, where each sector, and again, we're going to integrate from some theta 1 to some theta 2. And then we get polar area. So we have polar area, we have polar arc length, and then we can do the pre-calc stuff, where polar looks converging between x and theta, r and theta, and there's all sorts of polar graphs, but I'll look at. But so here are the big calculus things, right? Finding dy dx, finding dr d theta, and then this also lets us look at max and min distances. We want to find the maximum distance that's away. We want to find out when dr d theta is equal to 0, or the minimum distance when dr d theta is equal to 0, right? If you had some curve and you knew that dr d theta was 0 here, and it was positive here and negative here, right? This is the graph. This is some sign chart for dr d theta, and you could say then that this is some max. Right? That's when r is at a maximum, because dr d theta is growing and then it's decaying, so that must be some maximum. So we can use that. We certainly can look at dr dt based on some chain rule. Again, they'd have to give you some theta as a function of time, so you could find then d theta dt. We could find the arc length of some curve. So let's say we wanted to find the length of the spiral from here to here, right? We could integrate from 0 to 2 pi of this particular curve. Again, r is the actual given curve, and dr d theta is the derivative of that curve. We can find area in polar. We could find area of inside one and outside another by looking at like a washer technique. We can sometimes have some spiral in something else, and we can integrate so far and then integrate another. What about the intersection of two polar curves? That's another nice one. The intersection, or when does a polar curve get back to the origin? So the origin, and now we'll look at other things here in a second, but remember, r equals 0, then the object is back at the origin. So if you get a little confused on, when something spins back to the origin, you just got to figure out when r equals 0. And the intersection of the two curves are just when one r value equals the other r value, and that's actually pretty easy to do. Lots of times we have to solve this in Cartesian mode, because if you look at all the polar stuff on your calculator, you're not going to see that. But in terms of two curves intersecting each other, right, you could start out with r equals some circle. So r equals 3 cosine theta. That's some circle. It actually looks like this. And then you could have this. You could have a spiral. You could have a spiral start. I don't know, theta plus 1 or something. So that'd start like this and go like this. And if you wanted to find this intersection point, you would just set this r value equal to this r value, and then you'd actually graph it in Cartesian. So you flip your calculator back to Cartesian mode, and you're asking your calculator to find the x value at which those two things are equal. And x is just a number, just like theta is. It's just a number, and it's in radians, and it looks like, I don't know, this would be like, 1 radian or something. Okay, so this is the polar intro. I'm going to go ahead and pull up some, take a video of the actual computer when we're playing around with some polar graphs, and you can kind of see how everything kind of works.